So good morning, good afternoon, whichever time you have. Okay, I have to say out front that I don't do presentations very often. So if I get too nervous or something is unclear, please ask me questions and we can always follow up in the chat if I miss something in the talk. So the title of my talk is Designing an Optimal Strategy for GMAO S2S Ensemble Forecasts. And this is really what I will be talking about, the process of designing the strategy, how sort of take you through our thought process and our experiments, and eventually, hopefully in 20 minutes, you will understand why we propose the design the way it is now. And I also have to acknowledge and give credit to our wonderful S2S team, which is behind my work. They're wonderful people and too many to list on the title slide. So with that, I will move on and tell you why we need ensembles. So probably for this audience, I don't really need to do that. This is the schematic that you have seen many times with designing an initialization strategy for the system that we use to do forecasts that set of subseasonal forecasts that going out to 3 months, and then long range seasonal forecasts that go out to 9 months. And for the subseasonal forecasts, I don't know, do you see my mouse? So this orange range, the subseasonal forecast, the more critical is to initialize the atmosphere and capture the teleconnection modes. And for the long-term forecasts, we need to be able to predict the modes like ENSO. So so we want to study we want to understand the quality of the properties and the qualities of the ensemble and what they can help us learn about the predictability and improve that. So here I will tell you a little bit about our current system and how are we going to use that as a base for designing the new one. So we have an running coupled global analysis from which we initialize the forecast. And right now we are using for production the system that we call S2S version 2, which is very similar to S2S version 1, which we retired at the end of 2017. Similar in the sense they were designed in terms of initializing the ensemble forecasts. So here I'm showing you typical forecast months, and the little circles indicate times every 5 days. Every 5 days, we initialize the seasonal forecasts during the second half of the month. So these are long, solid orange lines. These are the seasonal, meaning 9 months long forecasts initialized from the unperturbed analysis state, and closer to the end of the month, the dashed line lines illustrate the ensemble members that initialized from the perturbed state. And this is also the time to introduce the terminology. So the solid lines would be the lagged ensemble members initialized from the unperturbed analysis state at the different times throughout the months, and the dashed orange lines show the burst ensemble members initialized at the same time, but from the perturbed initial conditions. The little short blue lines here, our subseasonal forecasts, which right now run out to 45 days, and they are initialized every 5 days. One member is from the unperturbed analysis, and additional 3 members from the perturbed analysis states. And right now, this subseasonal and seasonal forecasts are separate. The separate ensemble members, they run separately. In the future, we're thinking it would be logical to join these systems and run the subseasonal forecasts and then continue the same integration out to subseasonal. So I will tell you about that a little later. So, and down at the bottom is just an example of the one of the figures that we put out every month illustrating the forecasts, the seasonal forecasts. So again, here I show the Nino 3 SST index. The solid lines, the greenish lines, are the unperturbed members, the lagged ensemble members, and then the thin lines show the burst ensemble members, and the line with circles is the ensemble mean. So we want to understand what how good is our ensemble prediction. And one question that we can ask is the ensemble spread as an indicator of the forecast uncertainty? And there's a way to quantify that following the paper by Barton et al. We look at the ratio of the standard error of the estimate and the standard deviation of the intra-ensemble spread. And shown here on the right, the value of this R, of this ratio for the 2 systems, the older one, the S2S version 1, and the current production one, S2S version 2, for the Nino 3.4 SST index. And here on the bottom are the lead months, and on the right are the initialization months. So the forecast goes horizontally from left to right. And you can see that for the S2S version 1, most of the plot is kind of bluish greenish, which means the R was less than 1. So the system was what we would say under-dispersive. And the current production system, S2S version 2, for this system, R is a lot closer to 1 and actually goes above 1 in the spring for the long lead times. So the system becomes a little bit over-dispersive. So having learned that, we think, okay, for the early months, we kind of want to increase for the early leads, would like to increase the ensemble spread. And for the very long range forecast for this spring season, would like to kind of keep the spread under control if possible. So let's see what we can do about that. And so that's one question, the ensemble spread. The other question we need to consider when we're designing a new system is how big of an ensemble do we need? And the picture on the left is probably very familiar to many from Adams, Kafas, and Smith's paper, where they argue that for the subseasonal forecasts, we need large ensemble to improve ensemble mean scale. And shown here is the NAO scale versus ensemble size. So this tells us that we would need to have an ensemble of, ideally greater than 30 members. But that's all fine for the subseasonal forecast, but for the longer forecast, it's just technically impossible to have a large ensemble. So we want to understand whether we really need such a large ensemble for the seasonal forecast. And here I'm looking at the again, the Nino 3.4 index, its forecast, and on the right, there are two plots that both show the ensemble mean error versus the ensemble size, and we can assess that by doing repetitive forecasts. And I'm showing here on the bottom is the ensemble size from 5 members out to 35 members, and the size of the error shown on the left. The bars show the 90% confidence interval, and we estimated this value for many hindcasts for many years, different situations, El Niños, La Niña years, and realized that really the ensemble mean error doesn't vary with ensemble size, with a very rare exception shown on the bottom. But even here, the error usually saturates by with an ensemble size of 10 or 15. So that tells us that for the long range forecasts, we don't need an ensemble that is very large. So that leads us to an idea of doing the shorter forecast with a large ensemble size, and then somehow subsampling the ensemble and reducing it in size, and continuing for the long forecast with a small ensemble. Okay, so this slide just sort of again gives the summary of what questions we want to address when we are designing the new system. So we want to look at the different ways to initialize the ensemble, doing the perturbations, or maybe using combinations of lag and burst ensemble members. And we want to have a large ensemble at the beginning and then subsample it and continue with a few ensemble members. So then I will describe the methods we use to initialize the ensemble and introduce the synchronized multiple time lag approach, and describe in detail how we're going to subsample the ensemble. So right now in our production S2S version 2 system, just like in the previous system, we use the, when we do the burst ensemble members, we use the perturbations, we create the perturbations based on the difference of the ensemble states that are 5 days apart. But now we're thinking that maybe if we use the analysis snapshots that are separated by different number of days, that will allow us to capture the different modes of variability. So we will, here I'm just showing you an example of what types of variability that we may potentially capture. So on the left, there's the EF number 1 of potential temperature at 5 millibars for the states that are separated at 1 day, and it kind of shows the small scale synoptic variability. And at the bottom, same EF1 for the states that are separated by 5 days, and here you can see much larger patterns that are indicative of the teleconnections, that type of variability. And on the right, just as an example, the vertical slice of the ocean, and this is the temperature at the equator. You have one of the states that are separated by 1 day, show the variability in the thermocline, and if we look at the states that's separated by 10 days, we see very different sort of wave type variability. So by introducing perturbations based on this randomly chosen separations, we hope to introduce all these different modes of variability into our initial conditions. And but we want to make sure that we create our perturbations in such a way that they all have more or less the same amplitude. So we need to come up with the proper scaling, which would, which I will show you in the next slide. We can generate, we can compute the scaling factor such that our perturbations would be always about 10% of the climatological variability. And again, we looked at how to most comprehensively do that, and realized that we need to use different scaling factors for atmosphere and ocean. We can use the same factor for all the variables, but we think it would be best to use different scaling factors for different seasons because the climatological variability is different. Then we looked at the lag versus burst type of initialization, and here I'm showing you an example of the very first forecast with this S2S version 2 production system, which we started in at the end of 2017. It's probably not the best forecast. It's obviously not the best forecast because the black line is the observations, and the green forecast kind of miss it. But that's one reason is why we need to have a good ensemble, because we want to, if we have large errors, we have to have spread enough to capture them. So here I'm showing you the current S2S version 2 system, the lagged ensemble members, and the whiskers are the envelope of the ensemble, and the boxes is the standard deviation centered on the ensemble mean. So you can see how the largest is spread with the months, with the forecast months, and when I'm adding the 6 burst members, you can also see how in the beginning the burst members don't have a very large spread, but they seem to have a larger error growth as time goes by. So that gives us an indication that the burst and lag initialization procedures can give different error growth patterns. So now we begin our experiments, and these are the test forecast that we did. We created an ensemble of 40 members with atmospheric perturbations, and you can see how the error grows. It's very small at the beginning, but it seems to grow large. Same procedure, but when we only perturb the ocean variables, and here we create an exhaustive burst ensemble where we initialize 1 member per day. And in conclusion, we can say that it seems that the burst initialization strategy creates larger spread in the early leads, while the I'm sorry, the lagged members have larger spread in early leads, but the burst members sustain the error growth at the extended range forecasts. So we came up with an idea to how to create large ensemble in the beginning, but then we want to subsample that ensemble for the longer range, but ideally preserve its properties. So we came up with this stratified sampling algorithm, and the idea is to let the forecast run for some time, for 1 month or 2 months, then compute the strata using some clustering algorithm, and then subsample this strata proportionally to the population of the clusters. And on the right, we're showing the very large ensemble in the beginning with clusters color-coded by different colors, and a thick dashed line showing the cluster means. And at the bottom, subsampled ensemble with cluster means showing in the dotted line. And you can see that we pretty much capture the spread and different directions of error growth. We don't want to miss any. To quantify how good this procedure is, we can use Monte Carlo approach and look at the large ensemble that we're trying to subsample, look at its mean, and then subsample it using the stratified approach and reconstruct the ensemble mean and compare it to the just randomly sampling the large ensemble. So repeating this procedure thousands of times, we can come up with the variance of the reconstructed sample means using the random approach and using the stratified approach, and comparing the ratio of these two variances. The lower this number is, the better the stratification. And by looking at this R for different number of clusters, we can see which one is most optimal. And also we looked at this R for different periods in our forecast, which we use for the stratification. If we stratify early in the forecast during the first months, we really just looking at the distribution of in the initial conditions. So we figure out that it's best to let the forecast run for 2 months and use the second month of integration as a base for the stratification. Then this value R stays smaller, stays below 1 for longer, out to 5 months. So that's good. So this is the final strategy. This is what we're going to do for the version 3. So again, showing the typical months, every 5 days, we take the unperturbed analysis state and add, so that run one forecast from the unperturbed state, then add 4 perturbations using this SMT method for the atmosphere. And at the end of the month, we add 10 more perturbed states, 10 more burst states with ocean perturbations. Let all these 40 states combined run out to 2 months, then apply the stratified subsampling and choose 10 ensemble members that will be continued out to 9 months. So that's it. I know I'm over time, so I will stop here. Yeah.
Thank you, Anna. Thank you for your interesting talk. We are a bit running late, so let's move on to the next speaker, Frederic Vitart. And we also have a chat window, so if the audience has the questions to Anna, please write. Actually, we have one question. The next talk is about the lag ensemble versus fast and sampling strategies for subseasonal predictions.
Okay, can you hear me?
Yeah.
Okay, hi. So this is Frederic Vitart from ECMWF. Yes, so I will give a presentation on burst versus lag ensemble strategy for subseasonal prediction. So first of all, if we look at the configuration of the S2S models, and if we focus on the Ensemble Generation, we can see that there are two classes of models. The one in red, which are run once or twice a week, with a large ensemble size. So they are usually the forecasts are produced in burst mode, usually. And then we have other models which are run more frequently on a daily or sub-daily basis with a small ensemble size, typically 4 members. So since it's difficult to produce predictive forecasts with just 4 members, with those models, predictive forecasts are usually produced in a lag mode, so where you combine the forecast over the past forecast over several days, typically about a week. So if you combine a week, you get about 28 member ensembles. So, well, the question is it's not clear yet. It's not clear which one is the best strategy. Each of those approaches have advantages and inconvenience. An advantage of burst sampling is that for the same ensemble size, after lagging when applied, so normally the burst sample should be more skillful for the day when it is produced. I mean, as long as the ensemble has been properly generated. A second advantage of burst sampling is much easier to create products because all the members have the same start date, same lead time. Lag ensemble, however, has some advantages. Is that it's likely to be more skillful for the other day of the week, so you have more frequent updates. Another advantage is that since you combine several forecasts over several days, the evolution of your forecast from day to day is likely to be smoother, so less chance of abrupt changes from forecast to forecast, like we see sometimes with the burst ensembles, where we got sometimes a flip-flop, as we call behavior. So in this talk, I will focus on the ECMWF standard range forecast. So currently, those forecasts are produced in burst mode. We run a 51-member ensemble for 46 days, twice a week, every Monday and Thursday at 0Z. It is an extension of the medium range forecast, which is run at a resolution of about 18 kilometers up to day 15. And so the extension from day 15 to 46 is produced at a lower resolution at 36 kilometers about. The model is coupled to NEMO, a quarter of a degree every hour. And the initial conditions are produced from the operational 4D-var analysis with singular vectors on EDA perturbations. For the atmosphere, for the ocean, we use NEMO-var on wind stress perturbations. So the current configuration is the following one, is the top one here. So we run 51 ensemble member every Monday and Thursday. On the forecast for week N for a certain week, so a combination of all the 51 members starting the same date for the same deep time. And the question now is, could we replace this system by a lag ensemble where we run a model on the daily, with a daily frequency? And here the lag ensemble has 2 attributes. One is how many NE, which is the number of ensemble members we run per day, and ND, which is what is the optimal number of days we combine to produce a lag ensemble. The larger ND is larger is the ensemble, but on the other hand, you had all forecasts, so you have a negative impact on the t-score. So there has to be a sort of a balance, optimal value for ND. So the main question here we want to address is, so what is the minimum value of NE, so that the lag ensemble forecast is at least as skillful as the current system every Monday and Thursday. For the other day of the week, it's likely that the lag ensemble will be more skillful. So for that, we run an experiment, a 15-member ensemble that we run. So that was the larger reforecast, starting first 4 times a year for the period 1989-2016, with a resolution, operational resolution. And we reproduce the same run 1 day, 2 days, 3 days, 4 days earlier. So to be able to create a lag ensemble. So in this series, we compare those burst ensemble with the lag ensemble produced by combining several of those past forecasts. So if we first start with a Madden investigation, here we look at a comparison of a lag ensemble, which is produced by taking 5 members each day, compared to burst ensemble, which is 15 members. And we look at a different way to combine. We combine only 2 dates, 3 dates, 4 dates, or 5 dates. So of course, the ensemble size will increase with the longer time windows. So what we can see is that in the medium range, so this plot shows the difference of bivariate correlation for the MGO between those two systems. So negative means that the burst ensemble is more skillful, and positive means the lag ensemble is more skillful. So in the medium range, there is a degradation. Whichever combination you take, the burst ensemble up to for week 1 is at least always more skillful than the lag ensemble. Doesn't necessarily mean that the lag ensemble cannot be used for this time range, but then the window has to be much smaller than 24 hours. For the second week, it's a bit balanced, but in the longer lead time, actually, there seems to be an advantage actually to go for the lag ensemble. This may be helped by the fact that the model is strongly under-dispersive. The position of the MGO also tends to be, the ensemble tends to be too small in our burst ensemble. What we can see nicely is that as the lead time increases, the longer windows are also increasing. So for the last week, for instance, putting together 5 dates is slightly more skillful than putting together only 3 dates, for instance. If we look at scorecards, marginal skill scores, so here we look at the difference of CIPSS between the two configurations, so 3 days, so 5-member ensemble with a 3-day lag, which is roughly the same size as a 15-member burst. By the way, both systems will be the same cost, competitive cost. We can find that for the first week of an isotropics, there's a slight degradation with the lag ensemble, so the burst ensemble seems to be slightly better there. By the way, that's for 20 variables. We look for week 1 to week 4, and this is for Northern Hemisphere tropics. So blue means that the lag ensemble is more skillful, red is less skillful. And dark colors meaning the difference is statistically significant. So we can see that for the longer range, for week 2 to week 4, there's a slightly significant difference in the skill scores. Suggesting that if at ECMWF we are running 15 members twice a week, replacing the system by 5 members on a daily basis could be quite envisaged. Because not only the score will be neutral on Monday and Thursday, but it will be better other days of the week. So, but we're not running 15 members, we're running 51 members. And so the conclusion of the previous slide may not be suitable for the following reason, is that the impact of lag ensemble is to increase the forecasted score due to increase ensemble size, but to decrease also the forecasted score due to the deterioration of the initial conditions. The second one is independent on the ensemble size, while the first one is dependent on the ensemble size of the burst ensemble. If the impact of ensemble size on the forecasted score is not linear, is asymptotic. So if you double the size of the 50-member ensemble, this will have a larger impact on the probability scores than doubling a 51 ensemble member. In other words, it's much more difficult to beat a 51 ensemble member burst sample than a 15-1 burst sample. So we have 2 options. One is to redo the experiment with 51 members, which is a bit too costly. Another one is to use a formula to extrapolate the CIPSS, knowing what is the CIPSS with the 15 members. So for that, we use a formula from Ferro, defined by Ferro, which will tell you what is a CIPS for an ensemble of size capital M, if you know the CIPSS for another given ensemble size. There is some caveat to this formula, but it seems to work relatively well for the test we did for the first 15 members. And this formula allows us to compute all possible combinations, a formula combination of lag ensembles. And for each of those configurations, compute the difference of CIPSS between this lag ensemble, which is defined by any, the number of ensemble per day, which can go from 1 to 51, and the number ND, which is the number of lag days we put together, which is from 2 to 5. And so we do the difference of CIPSS with the CIPSS of the burst ensemble with 51 ensemble members. And we average that over the 20 variables. So this is the result here for the first, for week, what we call here week 1, which is in fact day 5 to 11. So in this plot, we see the difference of the APSS between a lag ensemble and burst for all possible combination or possible configuration of lag ensembles from 1 member to 51 member in the x-axis, on the number of lag days from 2 to 5 on the y-axis. On this line represent 15 members per day, which is the same cost, complete cost running 15 members per day than 51 members twice a week. So everything on the left is a cheaper configuration than the current system, and everything on the right will be more expensive. The black line represents the line of 51 member ensemble. So what we see is that for this time range, where the graphic is mostly blue, which means that the burst ensemble is always winning. So it's very difficult to beat the burst sample 51 member ensemble during this first week, at least when the time window is larger than 24 hours. The minimum configuration to get something at least as equivalent as the current system will be to run about 40 members every day, and to do a lag ensemble with the two dates. Now, if we look at other time ranges, so this is the 5 to 11 again. So the optimal, as I say, is 40 members to 2 days. As for the other lead time, we can start to see some red color. So there are configurations, for example, for this week 2, day 12 to 18. There are configurations of the lag ensemble which will outperform the burst ensemble on Monday and Thursday. And on this dot here represents the minimum configuration that will be at least equivalent to the burst ensemble. So this suggests here that the minimum configuration will be 20 members running every day. And the optimal number of lag days would be 3. After that, we get red. The red here is much to the right, to the green line, so which means that this configuration would be more expensive than computationally expensive than the current system, will be about 40% more costly. But on the other hand, it will provide a better forecast other day of the week, or more frequent updates. For longer time ranges, the 1925 and 2632, we can see that the impact of lag ensemble becomes more positive as the lead time extends. And with longer lead time, the optimal number of days to combine also is increasing. So it would be about 4 for day 1925, and we come to about 5 for day 2632. The minimum number of ensemble members to run will also decrease. It will be about 14 for day 1925, and about 13 members for day 2632, which is about the same cost, represent roughly the same cost as the current burst ensemble. So if we are focusing only on those two times 2 weeks forecast, then replacing the current system 51 member ensemble by 15 members every day will help provide the forecast as skillful on Monday and Thursday, and much more skillful other days of the week. For week 2, however, this is not the case, so we will need to run more ensemble members. So those results were for the Northern Extratropics. If we go to the tropics, we find that there is more benefits in the lag ensemble. Even for week 1, there is some configuration of the lag ensemble which will be more skillful than the burst ensemble. We will need about 32 members per day. So already with 25 members per day, we will already be about neutral compared to the current system. And on here again, the optimal number of lag days also tends to be larger in the tropics than in the northern extratropics. So that's a result that is quite consistent with results obtained previously in the literature for seasonal forecasting. So to conclude, so running the ECMWF model extended range forecast is on a daily basis instead of twice weekly with smaller ensemble size, so could be an option. As long as daily ensemble size is larger than 20 members. Using line ensemble also can also help improve skill of week 2, 3, and 4. And the ensemble size needs to be, of course, larger than the burst ensemble size generally. And the optimal number of lag days increases also with the lead time and in the tropics. So this study and other results also triggered some thought about the future configuration of the ECMWF forecast, extended range forecast. We'll have a new supercomputer in the coming years, which will be installed in Bologna, which will quite increase significantly the computational, which will increase computational power. And then the question was how we should use these additional computational resources. So the plan is to increase the vertical resolution, so from 91 vertical level to 137 vertical levels, which we found improve, produce some significant improvement in the forecasting score for the standard range forecast. One decision was actually which is quite a big change from a previous changes in the model configuration, is to keep the same horizontal resolution as now. To keep it at TCO 319 to about 36 kilometers. The reason being that when we compare the steel with, when we did some experiment with much higher resolution, like 18 kilometers, we didn't find any significant impact in the steel scores. So, and even when we run it at we did some run at a very high resolution at about 12 kilometer resolution. The results were also quite neutral. So instead of spending resources on horizontal resolution, we prefer to spend resources in the Ensemble configuration. And one change though will be to run the model on a daily basis, so every day at 0Z instead of twice weekly. The idea is also to increase Ensemble size and to run in fact 100 members on a daily basis, which will allow actually in the lag mode to produce a really very large Ensemble Ensemble size, to reach very high Ensemble size, 300 or 400 members. Another important change will be to currently the standard range forecast, as I mentioned earlier, is an extension and continuation of the medium range forecast. So here the idea will be to run it separately from the first 15 days medium range ensemble and to start at step 0. So every day at step 0 will produce 100 members at 36 kilometers. One advantage of this is, first of all, that we avoid its change of resolution at day 15, which can be damaging. Another advantage is for medium range forecast. It means that every day at 0Z, we will have 2 ensembles forecast, one high resolution ensemble, which will probably be at 9 or 10 kilometer resolution, so about 50 members, and then there will be a 100 members low resolution ensemble. So this opens the door to create a multi-resolution ensemble of 150 members. So the reforecast, it was a plan to run the reforecast on a daily basis instead of twice weekly, but with a lower ensemble size. Finally, I just want to mention that all those changes may not be introduced at the same time. So we plan to increase the vertical resolution quite soon this year. The other changes will come probably at the beginning of first implementation in when the supercomputer is in Bologna, and the reforecast may come slightly later. So I think I will stop here.
Thank you, Frederic. It's very useful for other modeling centers in designing the forecast system. We can take a few questions to Frederic.
Yep.
Any questions? If so, yeah, we also have the chat window. So if you have any questions, please write.
You're going to ask a question, Aaron?
Go ahead.
Thanks, Frederic. That's a very nice presentation. You said the optimal lagged ensemble changes is different in tropics and extratropics. And so how much is the difference?
Well, in terms of optimal windows, it's about one more day in the tropics, roughly. But yes, that's about day. So I mean, for week 2, I mean the optimal window for in the extratropics, as I show, is about 2 days. In the tropics, will be typically about 3 days.
Okay, so if you go in extratropics, if you go beyond 2 days, then you get a decrease in scale.
Exactly, yes.
All right, thanks.
And of course, this optimal number increases with the lead time.
Right, yeah.
Which means that if we want to do optimal products for different, it has to be configured a different way for different lead time for week 2 or week 4.
Yeah, it's a tough problem. It depends on variable, depends on geographical region, and a lot of things. So it's not a universal number.
Exactly, yeah.
Any questions? So thank you, Frederic. Let's move on to the next talk. I will share the Judith presentation.
Thank you so much. I'm Judith Berner. I'm relatively new to S2S, but I've worked on the medium range and on climate. I work at the National Center of Atmospheric Research, and so we're not a operational institution, but we're a research center. And one of the models we're having is the CSM, the Community Earth System models, which is used by the universities here in the United States, but also across the world. And so we're trying to develop a community model that can be run by many people. And we're also interested in community diagnostics. I call this towards the benefits of a stochastic parameterization on S2S forecasts and processes, because when I signed up to give this talk, I had assumed I have a lot more results than I do, but I will also tell you why. Next slide, please. So we've seen this before, this S2S predictability. Next slide, please. But I think of it not only as predictability, but also unpredictability or uncertainty. And so on the shorter time scales in ensemble forecasting, medium range, short ranges, I think ensemble systems are dominated by random model errors. Whereas on the longer lead times, on the right side, I think the models are dominated by systematic model errors. And one indication of that is that when we do S2S verification, we typically take the anomalies and do the verification of the anomalies, because that's where we can see skill. Whereas when we use full fields, the skill often goes down, and this is just a representation of the bias in the system. Next slide, please. So this is just, I thought this is an ensemble seminar, so I wanted to show one ensemble, just the schematic. So on the shorter time scales, we have stochastic parameterization or other model error schemes that tend to, are being developed to increase the spread. And so we have under-dispersive ensemble systems. If this is the case and you increase the spread, then you get more skillful forecasts, at least if you do not degrade the RMS error. Next slide, please. On the longer time scales, however, stochastic parameterization have the potential to change biases. So this here is a very old schematic of a potential well on the left side, double potential well, and the associated PDF underneath. And so if you introduce a perturbation, you will change the variance of the underlying PDF. But in this case, you sort of have that potential to go into this secondary potential well. And if you change, excuse me, if you look at the change in the mean depicted in panel D, you can see that that is one mechanism by which stochastic parameterization can change the mean of a system. And some examples are in this BAMS paper that came out in 2016, but there's many other examples throughout the literature of people that look at the impact of stochastic parameterizations. Just because we saw the talk before where the ENSO came up, we recently looked into how stochastic parameterizations change ENSO, and in our model, it actually decreased ENSO, made a better model. And there we really were able to dig in and truly understand what's going on. And we found that perturbations to the frequency of an oscillating system will lead to a decrease in variance. And so in this case, it decreased the ENSO bias and it made it better. But when we see this in general, we don't always know why, and we just need a lot of people working on this to understand in which cases stochastic parameterization improve mean biases. Next slide, please. So as I said, we are not a operational center, and we have only recently, very recently started initialized forecasts with the global model here, CSM, that is. And I think I always try to make the case that the S2S timescale is an opportunity for model development, because it is right at the verge between the scales where random model errors dominate and that where systematic errors dominate. Anna, no, please leave. Excuse me. It is 7:52 here, so it's very early. One advantage compared to climate simulation is there's more data to do verification on the S2S basis. And often these systematic biases often developed in the first weeks. So as they develop, we can look into them and we can try to get to remedy them before, without doing these long simulations of multiple years or decades or centennials. So, and then I mentioned already that the S2S verification is often done on anomalies. But obviously, if we have biases, and this is a picture that was in one of Tim Palmer's paper from the Lorentz attractor. So if you're in the upper left and you have a bias that brings you sort of in the middle of the diagram, then you will have very different predictability, both in the mean, but also in terms of the spread. And if our biases are such that we really sort of go from one large-scale state into another one that is associated with different predictability, then we're not able to remedy this by verifying on anomalies. We really have to fix the full model. Next slide, please. So these are the first efforts led by Jager Richter here at NCAR. And so we initialized the CSM model with just anomaly initializations. Started from ECMWF. The ocean is nudged towards observations. And but although we have such basic initialization strategies, because we're traditionally not initializing the climate model, we have here on the left side, this is the ACC of 2 meter temperature in the weeks 1, 2, 3, 4, and 5, 6. So we have positive anomaly correlation, and it is in the ballpark of that of the S2S models. It's also showed on the right panel. So this paper is in preparation, where we look at the global land and then North America. And we have 3 models here. This is CSM1. This is the older version. The newest one is CSM2. Those are the green colors. And then we have the WACM model, which is a high top model. So it has the stratosphere and the mesosphere, but it's often run at lower resolution. And the different colors are just if it's 5 or 10 ensemble members. But basically, we have a considerable skill, which is comparable to that of many S2S models. Next slide, please. So what we want to do is we want to implement SPPT into the CSM, and then we want to run a subseasonal verification in addition to traditional climatological process-based verifications to look at the impact. And what I'm showing now here are very preliminary results. It's based on 3 years, and I'm using pre-industrial forcing, so I have a constant forcing both in the control simulation and in the perturbed simulation. Next slide, please. So this is just looking at the space-time spectra. On the left is the control simulation. The middle is the one with STPT, and on the right one is verifying observations. And so what we want is we want to get this MJO peak that really ranges from wave number 0 to 10. And it is just too peaked in the control simulation. And based on these 3 years, there is some hope that we're improving this somewhat. There is clearly sort of more variability around wave numbers 2 to 5, etc. Next slide, please. Hey guys, not now, please. My apologies. So here is the lag longitude and lag latitude diagrams. So in terms of propagation across the maritime continent, we don't see a big impact. But if we look at the northward propagation, so if we look at the lower middle panel, we see that the northward propagation of the signal of the anomalies is more pronounced than in the control simulation, and that seems to be better when compared to observations. However, it might propagate too far north, and also there is a hint that maybe the frequency has changed. And so we will need to look into these results more deeply. Next slide, please. This is the life cycle of the Madden-Junior oscillation. And we see here the different phases. And I first wanted to show you the whole picture before we go to the next one. And I want to point out some regions. Next slide, please. So if we look here over South America, we see that there is a teleconnection pattern. It's a very weak one, but this one is better in the simulations with SPPT, so we see green colors rather than the yellow ones in the control simulation. And also, if we look at the maritime continent, it seems that the propagation speeds are somewhat better in the simulations with SPPT as in the control simulation. So these yellow areas are better aligned than in the control simulation. So there might be something. Next slide, please. Oh yeah, so what we are planning to do now is to repeat all these S2S simulations with the stochastic scheme. We want to do some more tuning. We want to make sure that the energy and water balances are correct. And then we want to redo all these simulations and then look at the traditional S2S verification metrics to look at the impact of the stochastic parameterizations in a more complete fashion. The reason why I thought I would be further with this, but I'm not, is that we are having the ISP summer colloquium and workshop, which was postponed from 2020 to 2021 on S2S Science. And so it will take place virtually on July 12th till the 23rd. We have also an associated workshop, which we will keep very small, and so by invitations only to the lecturers of the S2S workshop. And many of you on here are involved in one or the other. We will also have next slide, please. So the ISP Summer Colloquium, it's an NCAR summer school for students. We have decided to keep it live so that we have live, it's virtual, but it's going to be live so that we have the one-to-one interactions, and we're trying to make it really lively. So it'll be 25 to 30 students. Because it's NSF funding, the majority has to be from the United States, but there is also some spaces for international students. We will record all of the presentations and we will make all of the tutorials available so that if there is interest to go through this for students across the world, the materials will be available. Well, typically this is held here in Boulder, Colorado, and then people come. And so to make it worthwhile for the lecturers, we also wanted to have a workshop where the lecturers can then talk on a topic of their interest, in addition to giving a basic tutorial. And we have secured funding for this, but because of the pandemic, we can't spend the money. And so we are planning to have a second workshop, which will be in person. It has to be, excuse me, is a typo, it has to be before August 2022 due to the funding sources. And this one, we want to really open up, have a meeting here in Boulder, and we will also accept contributed talks. We want to give the summer school participants an opportunity to come and get some of this in-person and connectivity and networking that summer schools typically provide for that second workshop, but I hope to see many of you there. Next slide, please. This is the organizing committee. Next slide, please. And here's the tutorials that we're preparing. And so the ones in yellow is where I have spent a lot of time on. So we are going to develop a probabilistic verification package based on ClimPret. So these are all Python-based scripts using the Pangeo framework. And the idea is that we want to provide a number of community tools that do sort of the basic pre-processing of the data. They deal with removing, computing the anomalies, dealing with February 29th, and this is all done in Python, which has these parallel Dask servers. So there is parallel I/O, and it operates on these ZAR files, which is a new format that allows for parallel I/O. And if you do it right, it makes all these verifications incredibly fast. So if we compute a CRPS for 19 years, 10 ensemble members, it takes 2 minutes. So this is what we've been working on. ClimPret was developed by Riley Braley, but it's also a community tool originally for decadal predictions. We're adapting it. And what we really want is to make some scripts available that people can sort of do the basic pre-processing of S2S data, and then they can go and add a Python Jupyter book with the metric they're interested in, maybe monsoons, MJO, etc. So we will have the basic ones in there, and we will have some tutorials based on that, where the students can, for example, look at potential predictability and then state-dependent predictability. And I hope after the colloquium we will have nice plots like we've seen in the previous talks. We will also have a tutorial related to the machine learning challenge provided by S2S. We will not use the data that is proposed for this, but we will just use some of these other data sets, and we hope to learn something. So we will learn something about how transferable the learned things are. There will be a hydrology application, a US West Coast precipitation application, then the IRI process-based S2S diagnostic package, PyCPT, and maybe we will have an additional tutorial on the ARC score, which is developed in Australia, but we still need a lead for that. And we also need to deal with the different time zones. It has brought to my attention that there's other S2S tools out there that are used by many of the S2S members. When we started this, I was not aware of them. I think one difference potentially is that as part of this effort, we are looking into putting S2S data into the cloud. We are starting with the CSM simulations, but we are also working with IRI and Andrew to put the S2S, the SubX database into the cloud, and hopefully then work with Frederic and others to do the same for the S2S database. It's a big learning curve, so if you ever try to do something like this, ask me. It's good to hand over the knowledge to other people. But what this does is it basically goes and it looks, do I have this data on disk? And if not, it goes into the cloud and gets it from the cloud. And I hope that that will really enable people to look at S2S, even if they don't have a lot of HPC resources, because the data is in the cloud. Nowadays, you can get the computation, the Jupyter books in the cloud for a small fee. There's nonprofits who do that. And so the idea is to really make a community tool available for people to try out new things that don't have HPC resources. Next slide, please. I think this might be it. Thank you. So this is just some of these examples for PrimRed. It has these line plots, then it has maps as skill of function and lead time. And here the bottom right one is heat maps. So this is showing for CSM1 the skill of the initialized data on the left as function of the initial month. So we see, not surprisingly, that winter is more predictable than summer. Then the middle one is a persistence forecast, and then the right one, where it's red, shows you where the initialized prediction is more skillful than the persistence. And so we see that most of the skill is in winter rather than summer. That's where the benefits of having an initialized prediction really pay out, but not for the first 2 months for this particular sample, but then for the, sorry, not for the first days, but for longer lead times. And so these are the kind of plots that this Klimpred, or this package will spit out, and we will refine it, and hopefully by the summer have something that we can distribute to whoever is interested. Thanks very much.
Thank you, Judith. I think we are running a bit late, so yeah, let's move on to the next speaker. And again, there is one question to Judith, and the improving the representation of MJO over the MJO is very interesting, and yeah, I think so. Our final speaker is Dr. Matt Janiga. Please go ahead when you're ready. We see your screen.
All right. Can everyone hear me?
Yes.
Okay, good. So I'm going to be discussing some work that a lot of us at Naval Research Lab have been working on, both Monterey division, which is the atmospheric side, as well as the S2S oceanography side. And that is the Navy Earth System Prediction System. This is a coupled global ensemble consisting of atmospheric, sea ice, ocean, and waves. And the focus of my talk will be on how we have moved into an operational capability. And I'll also discuss, and that's version 1. And then I'll also discuss version 2 and future upgrades, which are in the pipeline. So the Navy, so prediction timescales, there's traditional hours to days, and that's the mesoscale and global atmosphere-only models that we've traditionally used. And those are relevant for individual tropical cyclones or high wind events, anything which would be a hazard to ships and various bases. And then we've also have a number of tools that our climate sections use for long-range planning. That's to do with climatology and historical analogs. But within that weeks to months window, there is this new system we're developing and continue to refine. That is the Navy Earth System Prediction Capability Ensemble. So Navy ESPC is it's built upon our current operational systems. So for the atmosphere, it uses our operational atmospheric model NavGem, and then for the ocean and sea ice, that's the global ocean forecasting system, which we have been using as a standalone ocean and sea ice forecasting system. But these have been brought together through the Earth System Modeling Framework in NWOPC. And more details on the Navy ESPC system are available in this paper by NCAR, which has the link there. So on August 31st, 2020, the system went operational. We're still working on products and stuff like that, but we do have some preliminary ones based on the MJO, sea ice, and some other things. So the current setup is a 16-number ensemble, and that is 37 kilometers, and effective resolution 60 levels, and the ocean is 112 degree, as well as the sea ice also 112 degree. And there's also a deterministic system which we've developed, but when that's going to be transitioned into operations is to be determined. So yeah, it's a very high resolution ocean compared to most S2S systems. But that's because the Navy has a lot of interest in the predictions of the ocean and sea ice, not just as boundary condition for the atmosphere, but for predicting the ocean and sea ice itself. So here we have some plots showing the Gulf Stream, as well as the Arctic sea ice from a forecast. So there's been a lot of updates that have been done to improve the MJO, which is one of the most important sources of predictability for S2S timescales. To improve the representation of the MJO, we replaced the operational NavGem simplified Arakawa-Schubert convection scheme with a modified version of King Rich. The new scheme incorporates both turbulence and dynamically forced modes. For the turbulence force convection, triggering is represented by mixed layer Richardson number. And then other added enhancements include a treatment of convective momentum transport, as well as modified representation of the updraft environment mixing. So you can see the NavGem 1.4 is the coupled physics, but a non-coupled simulation. There, that's the second from the left panel. Obviously, the unmodified obviously is not doing a very good job at all. And then Navy SPC, that's a coupled version of this 45-day forecast, able to capture the not just the first MJO there in November, but the second one in December. And then this is showing some violin plots showing forecast day where the correlation drops below 0.6. And it's on the range of 20 to 30 days, which is comparable to many of the other sectors, the EC51 Ensemble. This may be a little bit better than some of the other periods. So it's just 1 year, 2017. But I also did verification on 2020, and it definitely does fall below the model in that period. But definitely encouraging results for our first go at a subseasonal prediction system. Here's some plots showing a similar day where correlation drops below 0.6 for the AO, the AAO and AO and the PNA, and then you have predictability on the time scale 8 to 10 days. We've also looked a lot at the ocean temperature prediction scale. As I said, it's a very high resolution ocean. So in this case, for RMSEs of ocean temperature from 8 to 500 meters, you have predictability for the control number. That's only out to about 11 days. But for the ensemble, it's able to be climatology after 30 days over the oceans. And then you can see some of the largest areas of mean errors. They tend to be right in the mixed layer, right on the thermic line. Some of the changes that are in the pipeline. So the atmosphere will be upgraded to NavGem 2.1, and that includes a high altitude model. So the extension goes quite a bit up beyond the stratosphere. Includes climatological aerosols and the radiant heating associated with that. For the ocean, it now includes tides within the ocean model. The CS models would upgrade to CIS version 6. That seems to be a lot better with some of the thin layers of ice, which are during the transition seasons. Wave watch 3. So we'll now include a couple wave model, but that's only in the force sense. So the atmosphere, oceans, yes, are not forcing waves, but that will be also available sort of in line within the model. As well as there's some updates to the ensemble, which I will discuss in later slides. So the planned coupled model configuration for ESPC version 2. There will be a deterministic short-term model, which will be effective resolution of 13 kilometers. And that will also now be the resolution of the ensemble, upgraded from 37 kilometers ocean model, no change there, but there is an inclusion of tides. And then you have the wave model, which will be 1/8 degree for the deterministic and 1/4 degree for the ensemble. And the ensemble exact number of members and initialization frequency is still very much up to how much computational resource we have available when it says operational roughly the end of 2022. However, we're thinking something on the order of 30 members twice a week, which is an increase over the 16 members once a week, which we are currently running. And to improve the ensemble spread, the current operational ensemble is just an ensemble of data simulation. And in that case, we have perturbed observations, include Gaussian noise errors consistent with the observational error, and that definitely has a lack of spread. And two of the ways that we're addressing that is with stochastic kinetic energy backscatter and analysis correction-based additive inflation, which I'll discuss a little bit more on the next slide. So these, in combination, have a pretty significant improvement on the root mean squares, continuous ranked probability score, bias, variance of the ensemble, as well as anomaly correlation. And so this pie is just a summary scorecard, so adding up all the things on the grid, different regions, and then the metrics are 2-meter air temperature, 10-meter wind speed at 850 air temp, 500 millibar heights, and upper level jet stream winds. So now I'll talk a little bit more about Psi here. So what Psi does is we have the analysis corrections, and they give up from the short forecasts, and they give us a general sense of what the biases are, and then those analysis corrections are fed into the model as it's running as a tendency, and that acts to reduce the mean biases. And then there's also a random component of Psi, which is generated by randomly selected from these analysis errors, and that acts to increase the spread. So here is a scorecard showing the improvement in biases for the northern hemisphere, exotropics, subtropics, and then southern hemisphere. So you can see that overall things are more green than purple, so there is an overall positive impact. However, some of the areas where you have a negative impact, such as on tropical 850 temperatures, here you see the operational in gray, and so it starts off too warm and then it goes too cool, and as it's continuing to cool, it does at some point pass that zero bias line, but that's not really an indication of an improved model per se. But as you see on Psi, it doesn't have that starting off to a high and then going to low. It just slowly goes to a lower bias as those tendencies are fed in. And so this is just focusing on bias, but we do see improvements in root mean square errors, and then we have the spread as well due to the random component of the analysis corrections, which is fed into increased spread. So now I'm all going to show some plots showing the impact of Psi on tropical cyclone environments. So this is showing for the North Indian Ocean Basin, West Pac, East Pac, and Atlantic. This is for simulations for the summer of 2017. So you can see that overall, most regions at most lead times have a decrease in mean absolute bias. Anomaly correlation tends to decrease overall week 2 and week 3, although it's pretty noisy later on. RMSEs are generally reduced across the board. Reduction in OLR and shears due to the fact that in the operational model, it seems to be overactive convection over most of the monsoon regions, and there's this upper level outflow, which is acting to shear all the tropical cyclones. We also see overall reductions in RMSEs in mid-level relative humidity, as well as in low-level absolute vorticity for most basins and lead times. Something we've also looked at is atmospheric rivers. So this is just plot showing coefficient of water bias in operational. So you can see that it's dry in most regions over tropical oceans, and that is reduced in the side. And you can see that difference. It's quite a large difference in that in moisture bias, on the order of 30 to 50% in a lot of areas. And there's also large improvements in winds. Actually, we found that the improvements in winds tend to be a little bit more coherent than the improvements in humidity and OLR. That's not too unexpected. You have a short forecast based, which you're basing your analysis corrections on. You have a very quick sort of shock or adjustment for the convection as it's model spinning out. Whereas for winds, it's a little bit smoother. So that may be the case why we see a more consistent movement with winds. And then version 3, this is 4 years or beyond, where we plan to include Neptune model, which is our next generation atmospheric model, which is does a lot better for these systems where we anticipate be running on tens of thousands of processors. This is actually almost my not just a next generation atmospheric model, but a sort of a beyond the next generation, sort of a 2 generations ahead. This is based on as a flexible grid resolution, so that has the mesh refinement. A goal will be to have explicit convection with our atmospheric model, and this is a core which will support that. So yeah, that, I'll take any questions, and thank you.
Thank you, Matt. Any questions?
I don't know if I can see the chat, if there are any questions there.
Question, Andrew Molad. Curious about this Akai, Asai, I'm not sure how you pronounce it.
Asai, yeah.
Asai. So I typed it in the chat. Is there some place where we could read more about?
Yeah, so there's a paper by Will Crawford, which just came out in NCAR. We read more about that. Can you see my screen there?
Yeah.
So, yeah, so you should search Crawford NWR.
Okay.
You should see it.
So these increments that you add in a priori are computed from an atmosphere-only data simulation or something coupled, or?
Oh, it's from the loosely coupled data simulation where we have
Okay.
the atmosphere and then the ocean. I think Will Crawford might be on the line if you'd like to ask me more questions. Will, am I accurately summarizing that?
That's correct. Yeah, the increments we use for Psi here from the coupled system. So, yeah. In the case of the publication that's mentioned here, this is for that publication is for the atmosphere only system, which is where we tested it first. We're still working on a publication that incorporates the coupled system.
This sounds similar to some work that Sig Schubert at NASA did with some others. He's on the call here with our system. That's why the curiosity.
Yeah, we had some conversations long ago about this work, and actually I failed to follow up, so maybe now is the time.
Thanks.
Any other questions?
For TC prediction is your metric for the data string. So that's it's just for the whole basin, just the averaging the shear OLR. It's not centered on PCs. Yeah, we're currently looking at whether there's improvements in TC tracks or MJL. So that's the
Are there any other questions to Matt?
Is there any reason to keeping ocean vertical resolution to 41 OLs? From what I recall from the conversation with S2S, increasing the vertical resolution just was not worth the computational cost, which was pretty substantial. But they did look into it, and they just didn't see it didn't justify the cost. Yeah. Yeah, thanks, Ben.
How much does the ASI, the bias correction, improve the week 3, week 4 forecast over US CONUS?
That's not something I've looked at. Will, have you looked at that in terms of like CONUS to meter temperature?
So what was the question again? How does the SAI improve week 3 and 4 of what?
Over US, yeah, temperature precipitation forecast.
I see. Yeah, you know that's not. We typically break it out as Matt's shown it here. I do have those figures somewhere, but I can't say off the top of my head what the impact would be. But I think generally we see pretty consistent performance. You know, for what you're seeing for the northern extratropics here, I think you could comparatively assume similar results for CONUS.
Do you have a publication to expand the impacts on the forecast scale from this bias correction?
Yeah, that's the one right there where it has the DOI.
Oh, okay. All right.
We should have some forthcoming publications that also detail this work in the coupled system. So that again, that paper reference there is for the atmosphere only system, and that'll be some ensemble tests out to 10 days and some deterministic results out to 5 days. But of course, as I said, these extended range forecasts will be in hopefully a forthcoming publication.
Okay, thank you.
Okay, I think it's time to conclude. And I would like to thank all the speakers and the participants. And we would like to have another webinar on ensembles. So if you have any materials or talks to present here, please let me know. We can arrange another webinar. So thank you for joining today. See you next time.